So today I'm going to present early work on an attempt of verification in climate models, especially for an orchestrated software piece, which is a couplers in climate models. So to start with, what is a climate model? A global circulation model, which is a type of climate model, are these large-scale models that simulate Earth's climate over a period of time. And these models usually tend to use a lot of physical laws, be it your fluid dynamics or thermodynamics, and they use several numerical methods, and they operate on a large scale of observational data. And most of these climate models are implemented in large Fortran, and due to like huge computational demand that they have, and the codes run on supercomputers. And climate models are usually composed of many interacting submodels, be it your atmosphere, land, sea ice, or ocean models, which are sort of interacting with each other, exchanging data with each other. And each of these submodels run on a different grid, different time step, different spatial resolutions. Now, in this figure, we can see that there are 4 distinct climate models. And all of them, we can see that they are different subsystems operating with each other. And although the scientific goal of all of these climate models are sort of similar, but the architecture differ in how the model is orchestrated. For instance, in the first 3, we can see that the chemistry model is subsumed in atmosphere model, whereas in the last one we have a sea ice, which is subsumed in atmosphere. So there are like a difference in how the models are orchestrated together, but there is also sort of a similarities that is in the center of all of these climate models. You can see a coupler which is connected between the various subsystems. So what is a coupler? So it acts as a communication hub. So it helps in model interaction, where the data exchange is mediated between various submodels. And usually it performs various operations like field exchange between the models. It performs interpolation of data and conversion between one grid format to another grid format, and also the time synchronization when both of them are running in different time steps or different time intervals. How do we synchronize between 2 models? And coupler is the one which is performing a lot of these operations for different models. And so which is why it's very critical for any sort of reproducibility or scalability, and if you want to attempt for any correctness in multi-component simulations. And even some minor errors in coupler, be it your unit mismatch, that can easily propagate and distort some scientific results that we have from these climate models. So coupler correctness and verification in general. So verification of climate models is, people have very keen on this, but the only problem is they haven't get past testing or integration testing and a lot of validation. And the problem that here is verifying a full climate model is extremely complex because it's huge, millions of lines of code, and everything is written in legacy Fortran. And coupler represents as a very tractable verification target that you can attempt to see if there can be any sort of correctness that you can offer for many models at a time. So it makes a very high impact target. And even couplers are very complex, and they are loosely specified orchestration layer, because when couplers were originally constructed, they weren't designed with a formal verification in mind. So, which makes it also hard to ensure any sort of correctness or reproducibility or even maintenance. Maintenance is like if you have a whole climate model and if you want to replace just your atmosphere model, and how does that replacement work in the entire climate model? Does it offer any sort of correctness, or does it distort any sort of mismatches or any scientific results? Is a very interesting aspect to look into. And if with the previous picture, we saw that it's very similar to how software components work together. It's more like different modules are connected together, and it offers us to look into contracts or modular reasoning between the various models. Right now, there are these are the few major coupler frameworks that we have. One is CPL6 and CPL7 by NCAR, and we have the Earth System Modeling Framework, which also gives more like a very modularized framework for how do we communicate between the models. And in European models, widely used OASIS couplers. And MCT is more like an embedded library, which is being used in CPL 6 and 7 and OASIS coupler. It basically tells how the communication pattern is done between the various models, and also like how interpolation is done, for instance, or other different other operations is done using the library. Now, the couplers, in general, they vary in design, be it a standalone coupler. For example, ECMF is a standalone coupler, whereas the MCT is an embedded library. They have different data exchange pattern, different time, how timing synchronization is done varies differently, how it is implemented is different, and how interpolation is done is also different. Probably it's an offline interpolation or an online interpolation. So each couplers offer various ways of doing this. And it has also been evolved over decades with limited specification. And we looked into a bunch of these couplers, and based on some of these couplers, we identified some recurring tasks that could guide into a general design principles and like verifiable modules for these couplers. And some of the functional modules or the verifiable functional modules are configuration and initialization module, field registration and metadata module, grid manager and interpolation module, time synchronization, and data transfer and routing module. So these form a general design principle that any coupler should do. It's more like a coupler's generic tasks to perform. So we sort of extracted a tasks or a module task for each of these coupler modules. For instance, our configuration initialization module, what it does, it parses an external configuration file where you define your source or your target or various data that is included in your for coupling. And then you have a field registration and metadata module, which manages each coupling field and see that if it is registered and an associated metadata required for the coupling, be it your coupling frequency or timing interval, all of these data has to be registered if it is a field. And then you have a grid manager and interpolation module, so which defines various grids between the module, and you have to generate the interpolation weights for each other, and then you have to remap the grid. So for instance, if you have atmosphere data just flowing through an ocean model, so you have to remap the grid from atmosphere to ocean, right? So there has to be the coupler is the one which is doing the interpolation and then remapping the grid. And next we have the time synchronization module, which is coordinating the coupling schedule between various modules and how the coupling intervals is coordinated between them. And the last one is the data transfer and routing module, which is the one which is actually routing your information. Either you're doing an MPI transfer or is it a shared memory transfer. How the data exchanges actually happen is based on the communication pattern is handled during this module. So I'll show you one example with one of the modules and how we extracted these tasks in a form of a behavioral contracts at the level of modules. So for time synchronization module, here the example shows with contracts in form of requires, ensures, and invariants, which takes the form of your preconditions, your postconditions, or your invariants, where your precondition here says that the components are aligned and the clocks are consistent with each other, and your postcondition says that the data exchanged are once per step and there is no duplication with the time, and also the invariant here is the time monotonicity, saying that the time is always forward moving, which is an invariant for your whole module. And this usually, it's very common. We see that a lot happening in contract expressions using JML or ANSI specification language, which has been used with various behavior specification language, which enables these sort of contracts verification at the modular level. Now we have to address the elephant in the room, which is the Fortran dominance in climate modeling. So Los Alamos laboratory published a report saying that if you were to do some sort of migration of all the Fortran modules to Python, it would approximately take $15 million and several years of work. And still, it doesn't guarantee that it will have a bit-to-bit reproducibility, or you can't guarantee there can still be a lot of numerical mismatches. So there is no 100% guarantee that the migration will hold the validated legacy code that the Fortran has guaranteed so far for us. And there are some attempts to make some interoperability between Fortran and Python, which is available, but also comes with a lot of overhead, and they treat Fortran as a black box, and then you have an interface, and then you talk to the modern Python models. If we talk about verification, what's happening inside of verification? So Fortran lacks modern formal verification tools. So we have pharmacy for C, and we have key for language. These are the deductor verification tools, or we have Spark for Ada. But we don't have any deductive reasoning tools for Fortran, so it becomes very hard to prove any sort of automated correctness or automated reasoning for it. We have a small prototype which is done in Camford, which goes in the similar direction of providing some sort of deductive reasoning for Fortran. And Fortran also doesn't have any mechanized semantics, so it also becomes hard to come up with the tool. So if one were to start, they should actually start from the very beginning, which is giving a mechanized semantics for Fortran. So that's where the research is at the moment. Before I proceed to what we actually do, so I'll take a simple example, and I'll show how we try to solve this problem. So this is a simple coupler interaction flow between ocean to atmosphere through the coupler. And atmosphere and ocean models, they run independently on their own grid and their own time steps, but when ocean sends the data to the coupler does the processing for you, and it sends the data to atmosphere. The processing meaning if it's interpolation or time synchronization or other generic tasks that we saw so far. Now, what we propose is a dynamic contract verification at the coupler boundary, where the interaction actually happens with the coupler. So we insert our contracts or runtime assertions that we saw so far at the coupler boundary to check for the data consistency and data flow between the models. So this is more like what are the tasks, the generic tasks that you identified at the couplers. Now they are modified into, or they are captured in the form of module contracts. And these contracts are available at the coupler boundary, where the models actually send the data. And these runtime assertions make sure that the right data or the right form of data is passed between one model to another. So it sort of guarantees correctness in how the data is processing or how the data is exchanged based on your models of module contracts. But this also becomes difficult because of the poor integration with the legacy Fortran models. So what we do is we use the Fortran's ISOC binding for C that we have, and we wrap the Fortran with C, and we use pharmacy and its runtime verification plugin to verify these dynamic contracts, and these contracts sort of describe and validate the expected coupler interactions. So Fortran has this native support to the C, so it make it slightly easier. But if you, for example, how we have JNI for Java, which helps for two different models to, two different codes to communicate with each other, Fortran makes it easier to do it with C models. So the ISO-C binding sort of, you can wrap it easily, and then you can actually get the data for the dynamic contract verification. So far, to wrap up, we see that the couplers acts sort of a coordination hub that keeps various submodels working in synchronization, and they share very common behavior despite their different design architecture, and they can be captured as verifiable modules or verifiable contracts for different operations such as data exchange, timing, interpolation, and they form sort of a clearer design principles and for modular verification. So the idea is we can retrofit an existing couplers with these dynamic contracts, or if somebody's using a new age language such as Julia or Python to come up with a new couplers, you could use the same design principles and include the contracts in the language, and it's more like coming formal verification from the design. So it's a design by contract approach if you're thinking about a new coupler, but it could also work for retrofitting for existing Fortran models as well. So the next steps would be to actually build a minimal contract framework for existing couplers. So what I tried to did is with the Oasis coupler, which is open source and it's available and it's easily it has a lot of community support to be able to understand how the coupler actually works. It's not opaque at all, and what I'm trying to do is to have some sort of a contract framework for Oasis coupler and bridge some legacy Fortran system. And of course, I have to check the access, the reproducibility and performance, because it's a runtime verification technique, and how does it affect the performance is yet to be discovered. So you can find more details on our paper at PROPL workshop. So we did use a real runtime bug, which was found in one of the couple model, and we sort of assess how the error was developed, and then we see that how it could have been avoided if you had had some sort of contracts placed at the coupler boundaries. And we also mentioned all the modules and how these modules could be represented as your pre-post conditions and invariants for each of these modules. So it gives more like a design principles if one were to create new couplers, or if one were to generate these contracts. So yeah, that's pretty much the talk. Thanks.
Questions? Can you come up to the mic just so that the recording catches?
So you said already that you don't know how it will affect performance, but do you have a guess maybe? Because I think like these models are like ultra complicated, so maybe the part in between doesn't, in comparison, wouldn't matter that much.
Yeah. I mean, I'm not targeting something at the production level of understanding this. This is more at level of when you're actually testing, and at that time, a little bit of there is an expected overhead, of course, but I'm guessing it's a 2 to 5x of because it's a dynamic verification plugin of pharmacy, which comes with its own overhead. But I'm guessing a 2 to 4x of overhead, approximately.
So I have a minor kind of objection to the diagram here.
Yeah.
It kind of lends itself to a question about, like, you know, what is the right way to verify these types of scientific softwares in general, which is that when I think of a coupler, there's a part of me that thinks that, especially within the context of these various models where they're coupling at a boundary or something, that has like a precise mathematical meaning as, say, an interpolation operator or something like radial basis function interpolation. They have this whole vocabulary of these things in systems like precise. And what I kind sounds like these contracts are thinking more of like the data movement rather than like the commitment to that meaning, and that oftentimes part of the reason I have some confidence in the robustness of like lower level components, like just the finite element solver, is because it's pretty hard to fake a good convergence test. And so that thing would then maybe have, phrased that way, a good convergence test, or else some other property that would lend itself to testing and verification. So why not go there is kind of my question. Or is there like an example, or just a bug that you guys have found lend itself to this kind of more vision better?
So what maybe I stress more on the data exchange part here. So, but the coupler itself, okay, let me try to rephrase what you're trying to say. So is it more like, do this coupler feels, or the contract feels more orchestrated, or it doesn't really capture the real underlying conversion of how these models interact? Is that?
We'll put it another way. If I'm doing something like Gradle basis function interpolation, there's a precise mathematical meaning that roughly says something like, I have this point cloud data, this is the best approximation in some sense, that's the contract that should be honored, I can test this via various pathological cases, which hit the convergence boundary.
Yeah, but also like, that sort of happens, but this is a bit more high level, I would say, because let's say we take the same interpolation. And this carries, you still have your interpolation or a mathematical way of doing interpolation underneath, which has been validated, but we sort of put a behavior of how this interpolation should go from a one target to another. So I would say this is a bit more on a high level and doesn't really
Yeah, sure.
Yeah.